Hi, this is Professor Fernandez. We're going to work on class notes E in lesson 18. And the point of this class notes is really to show you the direction field of these two systems. And these are linear systems, so systems of the form x dot equals ax. We have solved these systems before. We know how to solve them using eigenvalues and eigenvectors. And in the next lesson, we're going to return to this system and kind of tie things together with the direction field, with the orbits, with the phase portrait, and the eigenvalue eigenvectors solution method that we know for linear systems. So this example is meant sort of to plant that seed of more plant some mysteries, if you will, of how the eigenvalue and eigenvector approach that we know for solving linear systems can tell us anything about the direction field or the particular patterns that we're going to see in the phase portraits in a minute. So what I've done is I've plotted these systems. I've put them into the website here, and I've already changed the numerical solver to Runge Kutta 4. So let's see what these systems look like. So let me pull that up. So this is the first system. X dot equals x minus 3y, and y dot equals negative 3 plus y. And I've set it to Runge Kutta 4. And I made the h value a little smaller. Again, this controls how many points essentially the numerical solver uses to try to draw the orbits the orbit through the point that I click on in the direction field. So you can see that there's some interesting dynamics going on here. So I'm just going to start clicking on the phase plane so that the system, the website can generate the orbits for me that start at the point that I click on. And it gets a little hard to get the interesting behavior near the origin, but I think you can kind of see what's going on. So you might recognize these types of curves as hyperbolas. So this particular system, its orbits seem to generate hyperbolic curves, hyperbolas. And again, we don't quite understand why. This is another instance of a phase portrait where we have seen, conic sections that you learned a long time ago, probably. Things like circles, ellipses, now we're seeing hyperbolas, and we don't really understand why, but they keep popping up in the examples that we're seeing for phase portraits. So now I'm going to switch to the second system. So this is minus x plus y minus x minus y for the system. Runge Kutta 4 set here. I left the h value as default because it turns out we don't need anything more than that to get some nice phase portrait here. So what I'm going to do, I'm now going to click on various points, and you see very, very different behavior from this system than the one we were just looking at. There are no hyperbolas here. There also aren't any circles or any ellipses like some of the other systems that we have seen. And you get this really pretty spiral pattern. So I refer to this phase portrait as almost like a black hole. Because I've been clicking as I've been talking everywhere in the phase plane, and it seems like no matter where I click, the system sends me to the same place. It just sends me to the origin. So if I widened my X range or my Y range, the same thing would happen. So this particular system ends up taking whatever initial points you click and just eventually sucking it into the origin along some orbit. And again, we don't have an understanding at this point of why the system is doing this and how we would know this by looking just at the equations of the system, right? That is certainly what is different between these two systems, the x dot and y dot right-hand sides. And again, going back to the lesson notes, these are linear systems. So what we do know how to do is we know how to solve them. These are x dot equals ax systems. We know how to solve them using eigenvalues and eigenvectors. So, if you have a hunch that the reason why, the orbits here are spirals, in, and the orbits here are these hyperbolas, then, if you have a hunch that this has to do with the matrix A, which is really the only difference between these two systems, and perhaps its eigenvalues or eigenvectors, then you are definitely on the right track. And we will fill in those details in the next lesson.